Hello, good morning. We'll get started. So today we are presenting how we worked at Machine Zone to sort of democratize data science capabilities across company using three of our core pillars of technology, Spark, Hive, and Druid. Brief introduction about us. My name is Pushkar, and I lead the data and marketing platform at Machine Zone. Later in the session, we'll be joining two of my colleagues, Igor and Michael. So a brief introduction about Machine Zone, who we are. So we have two business verticals, our game studio and our marketing platform, Cognant. Game Studio produces massive mobile games that break down linguistic and geographic barriers. These games are played across 180 countries, so you can imagine the scale of linguistic barrier that it has to cross. And in our game, we provide real-time message translation, which forms the core for people to interact with. Our performance marketing platform, Cognant, enables our own internal games. Our games are still the largest spender on the marketing platform. We also do media buying for external businesses. The scale of these media buying spans across 250 plus channels, including Google, Facebook, Twitter, and likewise. To enable this scale of buy, we have been working for last 3 to 4 years to build a data platform which supports our marketing technology platform. Just to give a sort of taste of the data currently we have at Machine Zone. So as it's very evident from the slide, Kafka, Hive, HDP in general forms the core of our data infrastructure along with Druid. So we have several clusters of Kafka, and they are basically categorized according to the purpose. Combined together, they are handling 40 billion messages a day. They have 250 plus topics, and combined, they are like 4,000 partitions. We have 3 Hadoop clusters, largest one spanning 300 nodes. We use Hortonworks distribution across all 3 of our clusters. Total unreplicated data size is around 5 petabytes. So how does this data comes in? Like, we have 2 sources, one which is our game, which is constantly ingesting data in real time. And then we are publishing ads across 100,000 apps, right, running in 200 countries. Together, they serve around 750 million impressions a day. And it fluctuates a lot. It's a seasonal data. It peaks sometime at close to 1 billion impressions per day. So combined, our data coming in from game, data coming in from our clients, data coming from these ad partners, all combined, we have 300 plus distinct source of data. Some of these sources are real time. We get data from real time, but majority of them ingest data in batch mode. Druid, which forms sort of core of our fast OLAP system, is currently holding 30 plus data sources. For those who are not familiar with Druid, each data source, think of them as a kind of a database in conventional way. They are holding 50 terabytes of unreplicated data again. Important thing to note here is when we say 50 terabytes of data, it's not the actual size of data that we have ingested in Druid. Druid does a fantastic job of reducing the size of data when you are ingesting. So the actual data is much, much larger than what is stored in Druid. So here is kind of an overview of how our presentation is going to span from here. So we are going to talk more in detail about how we sort of enable data science application. And for success of any data science or machine learning platform, the most important and critical aspect is data, right? So we will go in detail about how we do some of these ingestion at this large scale that ultimately feeds data to the marketing platform and our data science applications that we are running. We use variation of Lambda architecture in most of our applications. One of the reason being is our data and the way users look at data is constantly changing, right? So the first thing that we do is that no matter where we are getting data from, we store them in Hive as a kind of a immutable data set, and we constantly keep processing them and pushing it to the contextual store where it makes sense on a constant basis. So we will talk about data ingestion, how all of this 300 plus distinct sources of data mix into this immutable data store, which is Hive. The data as it comes from these distinct sources, they have a very different way of representing them, right? And we don't want to expose our user and our application to this diversity of data, right? So first thing that we do is that we normalize this data in the sense it makes a contextual meaning for our application. So different partner might be representing same information in different field or altogether different way. What we do is that we sort of unify the data at that level so that all the downstream applications have just one schema to deal with. We will, as a part of how we are democratizing our data science application at Machine Zone, we will talk in detail about the framework that we use for sort of model generation. And we will take an example and sort of try to show you how that predicts business values, right? Prediction of business value ranges from multiple things, like, for example, sometimes we are predicting what bid amount makes sense for a particular campaign, right? We are also running massive fraud detection pipelines, which sort of allows us to look at our media spend and categorize which one of them is a potential fraud, right? So far so good. We are able to predict some business outcome, right? But the way data enters from these 300 diverse sources, when actually the business actions are being translated, now you also need some sort of business intelligence layer to translate that action into what it makes sense across partners, right? For Google or for Facebook, it's altogether different how you create campaigns. Also, how the meaning of that prediction has to be interpreted is also different. So that's where we add a second layer of intelligence, which is comprised of our rule-based engine as well as some machine learning models that sort of derives the meaning out of that prediction and converts it into actual business action. We will talk towards the end about our data service framework. Our data service framework basically acts as a glue between all the system, from ingestion, from the optimization that we are trying to derive. It connects everything together and allows our business user to interact with this massive set of data. So I would like to invite Mike to talk about the other aspect. Thank you.
Hi there, I'm Mike. I'm going to talk about kind of the data ingestion, data normalization, and the machine learning platform that builds the sort of the foundational layer for what Pushkar was talking about earlier. I and my team built most of the foundation for that. So first I'm going to talk about the data ingestion layer. So in order to run media against, on over like 300 different ad networks, we've sort of had to build this unified data ingestion framework to bring in all of the data from all of these different ad partners, and it's all this ad spend and other side like impression, click, and install conversion data as well. So the majority of the data is coming in from these 4 different types. We have S3, Amazon S3. Our ad partners will give us like access to an S3 bucket with an access key and say, pull this bucket every day for new files. FTP servers, where they just give us direct access to file system for pulling that data. A majority of our, like, the more sophisticated partners have REST endpoints that you can do either, just to get the reporting, or, sort of an async job polling type system like Facebook or Yahoo and Google have set up. And for some of the less sophisticated partners, we have an email ingestion pipeline that sort of allows for them to send reports to an email inbox that we will scan and process and put into the raw store. So when any one of these data sets are ready to be ingested, our reader delegator will send some message out to one of the reader processors that will pull the data, or and then basically just send it off to one of the writer processes, which puts it into a time partitioned raw data store. So these are just time partitioned folders in HDFS. So this is just kind of a detail slide, talk a little bit more about each of these. So majority, again, of the ad partners that we run media for are sending us data through, or we're pulling data from their REST endpoints. But it sort of depends on their sophistication level as to whether they have that available, or we do kind of the S3 bucketing or FTP server pulls. So in this context, all of these, I didn't mention Kafka. So on the other side, we have like streaming data sets coming in from impressions, clicks, installs, conversion event type data, post-conversion event data. And I'll talk a little bit about the streaming pipeline in a second. But so a majority of this is, this side of the data set is pulling in ad spend and how it relates to like campaigns, and then stored and not normalized yet. This is just in its raw format as it comes in from the ad network that we're running the campaigns on. So this is a sort of high-level overview of the data normalization architecture. So in the kind of left side here, we have the sort of RT, like real-time ingestion, which would be like streaming data sets coming in. The data normalization layer is used for both ad spend and for normalizing the click, impression, and install data. So the RT event is data coming in from Kafka that's fed through like web servers that are used to send postback data from each of the like ad partners or attribution providers that we're working with for, depending on either for internal games or for MZ clients or external clients. So for the reading from the raw store, this is like sort of, it's used like in batch mode. So we have like the streaming ingestion, and then there's also batch mode. So they use the same thing, Lambda, whatever. So that's great. And when a data is sent into the normalization layer, it goes into our rule-based transformation engine. We have kind of a sort of data discovery portion where we inspect the event and say, hey, what type of event am I? And then that passes into this rules loader, which then will go and load whichever transformation rules need to be applied to that specific piece of data. Those rules are then parsed into a set of like functions. Those functions, you can think of them as like UDFs to apply to a data record. And then the rules applier is how we perform those transformations. So once the transformations have taken place, we send the data to 2 different locations. If it's like the real-time streaming data, it's sent back to Kafka, and Tranquility picks it up and sends it into Druid, which is our sort of reporting, real-time reporting system. And then we also write to HDFS so this will be like the normalized transformed reports. And so let's see, what's next? This is, okay, so kind of a little bit more detail about the normalization phase. So the streaming real-time source, again, it's Kafka. We use Spark Streaming. The Spark Streaming leverages the same transformation library as the batch does. The data is transformed and then sent to Kafka again, picked up by Tranquility and sent into Druid. For the batch historical backfill, so generally, like, why we need to reprocess data is one of the transformation rules may have been incorrectly configured, or we have a new set of transformations because majority of the input data set may be like 200-300 columns wide, but our eventual report doesn't have that many columns. So when somebody decides, okay, we actually need access to this particular column from this source, we add the transformation rule and reprocess the data to surface that in the report. So the rule-based transformation engine, it's so Apache Spark is the runtime, but the engine's built in Java, and basically we define kind of a custom DDL for transformation rules. Here kind of is just a simple example of what one might look like. So in this instance, it's a concatenation rule. The destination column, creative dimensions. We have input columns, creative height, creative width, and we're going to join them by a delimiter, an x. So this would be creative width, x, creative height, the values in the columns, not those exact strings. So that's kind of the data normalization layer. So after we've ingested the data, stored it in raw, like picked it up and normalized it and stored it in our transform data set, then comes kind of the fun part. We pull in kind of this data, and our data scientist will basically build a number of models to run to do predictions. So just sort of a brief overview of what the processes are involved with doing that. So we built the platform on top of Spark ML. The different components involved with it is firstly, the feature engineering, so extracting so after the data's been normalized, then a secondary transformation is done on top of that data set by whatever model that the data science wants to use, and deciding which features are going to be used and what transformations are then applied to those features is all encompassed within the feature engineering. Then there's the model training portion, which is once the features have been extracted, depending on what type of model. Generally, they've been using XGBoost or LightGBM for their classification. Training that data and then generating a set of predictions. So those predictions are then stored somewhere, and then comes the portion where we need to tune and test and iterate on the model. So after the prediction has been generated, those are stored, and then they can be measured against what actuals ended up being, and compared with other iterations of the model. And we generally have a visualization layer that we plot those, and I'll show a little bit of that later. And then deployment of the model. So once we've decided a model is good, ready for production, then we deploy it and run it. So in order to be able to do the feature engineering that our data scientists needed to do, we had to make a couple of extensions to Spark ML to make it work for their specific use cases. and also to enable them to work a little bit faster than just writing the normal standard library stuff that SparkML provides. This code right here is a little example of kind of a transformer. And so if you're not familiar with like SparkML's like processing, for the context of our predictions, we have estimators and transformers. An estimator is fit against the data set to generate a transformer, which is then used to either generate a prediction or transform a data set so that you can then generate a prediction. And so the example one that I'm showing here is kind of an aggregator. So in general, like the SparkML provides a SQL transformer. SQL transformer can do all of this, but it's harder to test, so we wrote one. This one in particular is an aggregator. It's a numeric aggregator. And so at the top, you see we've defined kind of a data set. There's a couple of columns, and the important column you can see is the key. The first one is like 1, 1, 1, and then 2, 2, 2. So when we create our numeric aggregator, we're going to set the grouping columns as like the first column, the aggregate columns as the subsequent columns that we want to aggregate, and then we're going to like provide a list of functions for each aggregate column as to what transformation we want to apply. And so once we transform the data, you can see like an output generated there. Just really shortly, 2, the min number for the 2 set of records is 4, and that's what shows up in there. And for number 1, the min is 4, or min is 1, and you can see that that's what gets output. So another thing that's pretty common is TF-IDF for feature engineering. And for our purposes, we had a number of, in our data set, we had several columns that needed TF-IDF to be applied to them. And performing the TF-IDF on each individual column was taking a long time, so rapidly iterating on building these feature stores was difficult without adding this extension, which was the ability to do parallel TF-IDF. So that's been really useful. It took like transformation time from depending on the data size. For one example, we had one that took about an hour to do TF-IDF, got down to 4 minutes through the parallelization, which is great. Anytime you can make things faster. So in this case, you can see we define some set of term columns and then create a parallel count vectorizer, say, here's the set of input columns that we would like to perform I didn't do the IDF, but just the term frequency here, and then basically perform the transform against this. And this is just the output notation of what the count vectorizer does in Spark. So that is the the IDF, parallel IDF to do TF-IDF is essentially the same set of steps. You just take the output of the parallel count vectorizer and pipe it into the parallel IDF. So another thing that, this is probably the more significant change to SparkML that we made, not change, but just extension that allows us to build more complex pipelines for doing feature engineering. SparkML, if you're not familiar, has a concept of pipelines. Those pipelines are generally linear. You can create linear pipelines and separately join them yourself. But what we wanted to do was be able to create and test one pipeline that allowed for kind of multiple, not just this example has one input, but multiple input data sources that can then be joined and tested independently as one unit, and then also in their subunits. So in this example, we create what's called a DAG pipeline, some generation of an input data frame. You have a number of transformers, so one could be like a binarizer or a set of pipelines independently. And then we have to wrap a joiner node, which will take these input, or the outputs of a given node and join them together. So you can see for like the N1, N2, and N3, one's a transformer node and the other two are estimator nodes. Those are sort of aligned with SparkML's kind of estimator transformer interfaces. And then the joiner node's defined, and then you just create a DAG pipeline, you set your nodes, and you define your edges, and kind of you can run your fit and transform. And the output graph looks something like this. What isn't shown up here is the ability to support multi-data source inputs for the DAG. This is difficult to sort of using the SparkML interfaces. Because they only work on one input data set, we sort of had to build something else. So what we have this concept of an identity node. That identity node contains a reference to the data set, which is then used, and you can create a DAG using that. And the identity node then sends its data set to the next node. And that's how the DAG pipeline works. Once we've done the feature engineering portion, we have the model testing and tuning portion. So once the features have been extracted from the normalized data set, they're put into the feature store. The feature store just allows us to rapidly iterate on the model testing because you can just load up a set of features and not reprocess through the feature extraction pipeline again to do the training and testing. So that's helpful. And we also do have configurable split testing, which says how much you want to use for training, how much you want to use for testing. So SparkML has a nice ML writable interface that allows you to store a model. So we've extended that to support our DAG pipeline and all the other feature extraction things that I mentioned earlier, so that we can save these and version them and pull them up and run them against new data sets and compare them with old ones. So then we, through this, generate a set of predictions, and they can be used. They can be generated using any version of the same type of model. If you change the model, you may have to reprocess your features to work for that model. And then we use them to compare across model implementations. And so how do we do that? Since we're using HTTP, we have Zeppelin available to us, which is a great tool for doing, writing notebooks for running a lot of these things. This isn't a notebook per se, but mostly the notebook is used for when we deploy the model, we can deploy it using Zeppelin, and then we can store it and version it. And then because Zeppelin has a built-in visualization library, you can basically pull data from some data store and plot it against another data set that you ran a prediction set for and compare them. So this is just an example graph showing kind of these are bucketed predictions sorted and then compared to Model 1 and Model 2 and then actual. So you can see Model 2 is showing a much better curve against what the actual was. So I don't have the exact model, but you get the idea. So yeah, the graphing library allows for great instant visual feedback when we're doing this. And then we use the notebooks for not only generating the output data sets, but also to test things against. And yeah, so once we've generated these predictions, they have to be sent somewhere else. And so Igor is going to talk about how the next steps work.
Thank you, Mike. My name is Igor, and I'm software engineer at MZ for 3.5 years. And when I just joined MZ, my company already did massive marketing, buying ads on a lot of different ad partners. And at that time, we just, as data platform, we provided just some reports how our marketing performs, is it good or bad? So, and then our marketing team, they consume these like reports, and like they basically did buying on different ad partners. After that, like we built kind of first layer of intelligence, like what Michael just mentioned. So we built this machine learning platform, which allowed us to produce predictions, like how most likely our campaigns will behave in future. So we could make decisions much early. But basically, what the like business values of predictions? Like it's not much, right? Like we need to decide what business actions we have to take based on these predictions. And this is like, and like what's our ultimate goal as a company? We want to make like this process of media buying completely automatic. Like, so like no humans should be involved in this process. So, and this is like where we start build this second layer of intelligence. So like our ultimate goal was to consume whatever machine learning platform produced and convert it into some business actions which our platform or like entire like data platform can eventually like deliver to our partners and execute it there. So, and then like what is partner instructions? Like for us, like we call partner instructions, it's set of commands which a partner can and should execute on his side, right? Like when we say partner, it's like Facebook, Google, right? And we're talking about like create campaign on Facebook or like change bid price, change budget, like relocate like some money across like different countries and like maybe change creatives. Like we know that, for example, like picture with like, I don't know, like military guy like performs like very well for like male audience, but it doesn't like perform like well for like women. And we at MZ, we do marketing at massive scale. So basically, like humans would not be able to create this like massive amount of campaigns. So we need to set up process to kind of like initialize like our campaigns, right? And to initialize just one campaign, you have to decide what bid price you should assign to this campaign, what total budget should be for your campaign, what targeting you would choose, and then basically which creative asset to select for this particular targeting group. So when like these thousands of campaigns, like let's say like they already been created, we start to receive feedback from our partners, like how every campaign performed. Like do we meet our KPIs or we don't? Like maybe, you know, like in this country, like this particular campaign like doesn't like behave like well. So we need in some like automatic fashion like shut down this campaign and reallocate this available money to another campaigns like where we like meet our KPIs. So again, like we need to probably like increase or decrease bid price for some particular campaigns, or like completely like shift budget from like one country to another, or like from one group of users to another group of users. Or like we know that, I don't know, like this picture or like this video like doesn't perform at all, right? Like we want to shut down such campaigns with this video and like replace them with, I don't know, like maybe new creatives. So basically, like this is the kind of like overall scheme of like this process. So we have output from our machine learning models. It is like whatever like Mike described, some like fraud detection, like predictions, like maybe some like other, like for example, for creatives, we do like something like A/B testing. Like we try to like predict like which creative will perform better. And then we also join this data with like our historical, like what was like the historical performance for these campaigns. So when we combine like these two different data sets and we ingest it like either to initializer or optimizer, then applying some like clustering algorithms or just like basically do a very simple aggregation, we can produce these ad partner instructions and then send them to our ad partners. So, and when we just like started to build like whole this data platform, we are faced with following questions. Like, where we will store metadata for our data pipelines, where we will store these instructions, and how we will deliver these instructions to our partners. And to kind of to accommodate like these requirements, we decided to like build framework for like microservice framework, which would allow us to like very easily and like rapidly build like new microservices, which like later will be used in whole this ecosystem. So, example of such microservices would be like to store some metadata about it partners, like I don't know, like what the some like information about Facebook, Google, Twitter, therefore. Metadata about campaigns, like when campaign was created, what was the bid price, and like what was the targeting. ASP, it's attribution service providers, like which give us attribution data. Also, like we need some metadata about them, and of course, at partner instruction service. It's basically the microservice which gets from our machine learning platform these instructions and send them to partners. And basically, I think like we decided to use like pretty standard stack of technologies for our data services. Like as interface, like we use REST API. Like it's all powered by Spring Boot. We deploy our microservices to Kubernetes cluster, our internal Kubernetes cluster powered by OpenShift. And like we invested a lot of time to make this process like as much automated as possible. So we leverage Gradle and Jenkins pipelines to do our like CI/CD like things. So like just like to connect like all these components like which we mentioned like during this presentation. Like our ultimate goal was to build this like data like feedback loop. So it all starts with like our data ingestion platform. Like we ingest data and then like send it to our data normalization platform. From after normalization, our machine learning platform can like take this data and like produce some like predictions or like whatever like output of our models. It goes to like data services, and like as I mentioned like before, like data services also powers our data normalization pipelines. And then when we get this final partner instructions, we send them to a partner, and then like we again like pull from our partners like all this like data and like repeat this process again and again, so we can kind of like iterate multiple times, learn from feedback, and improve our models and like basically like make our business like more successful. That's it from us. Questions? Yeah, so basically we, machine learning platform, like data models, like they produce predictions. We ingest them back to like our, to Hive to kind of like, we join them with our historical data so we can see like in advance what will be a result for like every campaign. And then we have like special team like of data scientists who consume this data and they apply as I mentioned, like some like k-means clustering or aggregation. They also do, I think, like some A/B testing and produce instructions. But it's mostly like some Python scripts which does this.
You won't use something like Simplex or anything?
No, not for now.
to do the parallel TF-IDF. If you look at the Spark ML code for how the TF-IDF is implemented, oh, our time's up. Sorry. You can talk to me after, but thanks for coming, guys.